Okay, so today we're going to talk about well, probabilities more, including tree diagrams, which this gets kind of tough. I feel like this is a tougher area. That's the homework from the other day. So start with what's called the general multiplication rule. Um, Go to write down the formula. It is on your formula sheet if you choose to use it. Remember that line, that vertical line means probability B given that A has already happened. So you have to basically adjust the second probability. When two things are happening, you have to make an adjustment to the second. It's something you've probably done without using a formula. Okay, so let's just start with the basic problem here. I think it'll make sense. A bag contains 5 red marbles and 8 yellow marbles. Suppose you randomly select 2 marbles from the bag. What's the probability that both are red? So if I'm working this problem, what I would do is something like this. So you're kind of drawing two lines. You're multiplying two things together to get your answer. The probability the first one is red would be, it looks like it's going to be a fraction 5 red divided by 13 total. That's the probability of A, right, in the formula. The second one is the probability of A given that B has happened, right? So in other words, in this case, it's what's the probability of A given that A has already happened in a sense. So 513, so we pick one red marble. There's no replacement. The bag has one less marble that it used to have in there, right? So there's no longer 5 red marbles in there. I'm holding one in my hand. So the second one, there's a 4 out of 12 chance. And that's what we're talking about. And then you just multiply those in your calculator to get your answer. But making that adjustment here, those are not independent events, those are dependent events. And so we're going to use the general multiplication rule. They wrote it this way. What's probably getting the first marble red? 5 out of 13. And then given that we've already picked one red marble, the second one would be 4 out of 12. And you get your answer. Okay, now a tree diagram. This is where this gets a little bit of a tougher kind of lesson here. So let me get this ready for the next one. We get a clear thing. Okay, so I'm going to use this. Okay, so a tree diagram. This is kind of a classic example. Okay, so kind of an easy one too. Shannon hits the snooze button on her alarm 60% of the school days. If she hits a snooze, it isn't always as obvious as this question that that's the second part. But that one's, yeah, if she hits a snooze, there's a 70% chance she, so let's start this tree diagram from the start. So it looks like the starting thing is definitely, she hits snooze on 60%. So we're going to call this snooze on 60% of school days. So that means by default, this is no snooze. She just wakes up. So that's kind of the first branch of the diagram. Now, if she hits snooze, so we're breaking off of this one, right? If she hits snooze, there's a 70% chance she will make it to class on time. So 0.7, this is going to be on time. And which means by default, 0.3 would be late. If she doesn't hit snooze and gets up right away, there's a 90% probability she will make it to class on time. Oh, that's so nice. So 90% she's on time, which means by default, it has to add up to 100%. Each time, do you see these branches? 0.6, 0.4, they add up to 100%. 0.7, 0.3, they add up to 100%. 0.9, 90%, and 10%. So that's going to be the late folks. Now, they don't tell you to do this, but I'm telling you this is a smart move. So at this point, you want to multiply all these. So this would be 0.6 times 0.7, which is 0.42. The chance of both of those things happening, snoozing and on time, is 42%. you just multiply the branches. So 0.6 times 0.3 is 0.18. So there's an 18% chance that you snooze and you're late. I'm just doing this by all of them. So 0.4 times 0.9. I don't know which one I'm going to use here as far as the answering the question. Is 0.36, and then 0.4 times 0.1 is, I think that's 0.04. If I added all those up, you should get 1, right? 50, that's 0.6, 0.96, it does add up to 1. So that means we did it correctly. So now I know the chance of each one of those combinations happening, right? So the tree diagram models that situation. Ours is a little bit better because it has the results of every outcome on there. It's going to make it easier to do. Did they ask a question? I don't think they've asked the question yet. They should have asked a question, follow-up question there, like, what's the probability that she's late? I think they didn't say the words of that, but so the probability that they're late, you would just look at these and go, okay, probably they're late. That would be the 0.18 plus the 0.04 there, because those are both the late. So 0.22 or 22% chance of being late. What's the chance of being on time? 0.42 plus 0.36. So 78% chance of being on time that way. They could ask other questions, but we're going to use those 4 answers to answer whatever questions they ask. They just didn't ask a question this one. They just had the tree diagram. Okay, let me clear that off and get ready for the next one. So for the 20% of people, US 18 to 36. So let's just kind of start that off here. So some folks are 18 to 36. 18 to 36. That's 20%. Then there's 37 through 48. That's 0.20, 25, 25. And then there's 49 to 67. That's 0.21. Is there more? Yeah. So they split them up into 4 groups to start with. This is 68 plus, and that's a chance of 17%. And those 4 numbers should add up to, did I miss one? 18 to 36, 25%, 37 to 48, 21%, from 49 to 67, and 17%. So I guess they left out the young folks there because it doesn't add up to 100%. But we're not going to worry about that right now. But I guess the leftover would be the young folks, but it wasn't part of the study, I guess. But according to a Census Bureau, 34% of U.S. adults age 18 to 36 oh, maybe I didn't do this right. Okay, so let's redo this. Okay, so let me get this out. Yeah, sometimes it's hard to figure out from the question. I didn't read the whole question first. That's what I should have done. Which one's the first branch here? And so it's not always obvious. Like that first example, it was kind of obvious. This one, I didn't read the whole question. I just assumed they started with the first branch, but they really didn't. It looks like the first branch is the age group. The second one is, do you read ebooks or not? So let me get the percentages right. The first one's the age group. So 34% of US adults are 18 to 36, so 0.34. 22% are 37, so 0.22. 30% are 49 through 67, so 0.3. I'm going to put 3 just so it makes more sense, but it's 0.3. And then 14% are the other one, 14%. Let's see if those add up to, now those I think do, 6, 7, 8, 9, right? So 5, 6, 7, 8, 9. Yeah, those add up to 100%. That makes sense. The first one I was like, something's wrong, right? Sometimes you kind of catch your errors, I made an error in the first part. So it's not always obvious what the first branch is. You have to kind of like experiment and make sure you understand the problem before you kind of get that first branch wrong, and then you'd have to start over. So now the second part that comes out of this is what they started talking about, which is that's the percent that read ebooks, uh, more ebooks than print books. So I'm going to call this one ebooks. So what percentage of folks do more ebooks? And so that first one, it is 20%. Ooh, so print, I'm going to say print is the leader, there's 0.8, so 80%. So that group much prefer the print there. So I'm just going to put E here and a P here for print, just because of room here. So the second group, 25% prefer, so 0.25, which means 0.75 is here. And ebook and print for this one, so E and P for print. So ebook on the next age group is 0.21, which means 0.79 is the other one. And then the last one is 14% our ebook here. So 0.14, and which means 0.86 is the print. Okay, so now we're going to go ahead, and they don't tell us to do this, but I'm telling you, it's a great idea to do this. So you want to multiply 0.34 times 0.2. So that's 0.068, I think. This one, you want to multiply 0.34 times 0.8. And you might have to get your calculator out. So 0.34 times 0.8 is 0.272. And then this one would be 0.22 times 0.25. .055. And this one's 0.22 times 0.75. You're multiplying the branches there. And it really helps to do that. We might not use all of them. .165. And then 0.3 times 0.21. 0.063. And then 0.3 times 0.79. So 0.3 0.237. Point 0.0196. Point 0.1204. That was 0.14 times 0.86. Okay, so we have all those numbers. Let's see what the question is. We can use those to answer it. Suppose we select one U.S. adult at random and record which age group the person is from and whether they read more ebooks and print books. Draw a tree diagram. We did that. Ours is better than theirs because we have all the results. The question is, the age categories go in the first set of branches because the given relative frequencies are not conditional probabilities. The second one was conditional on the age group. Because the relative frequencies for reading more ebooks and reading more print books are conditional of the age categories, the reading tendencies go on the second set of branches. So that was the trouble, is figure out sometimes which one's the second set of branches. You kind of look at both of them, say which one's more conditional. That's the one on the right. That's the second layer there. Find the probability that the person reads more ebooks than print books. So all you would do for that one, more ebooks, you would add up this number plus this number plus this number plus this number, I believe. Right? So more ebooks, which are those four numbers we had, and it's 0.2098. So we had already done the first part of that work there because we went and just multiplied every branch, which is a smart move. So many women choose to have annual mammograms to screen for breast cancer starting at age 40. Unfortunately, mammogram isn't foolproof. Sometimes the test suggests a woman has breast cancer when she really doesn't. It's called a false positive. Other times you get what's called a false negative, which both are bad. Which is worse there? So if you had a woman, the test says you have breast cancer, but you don't. Ooh, that would be weird, right? So that would be bad. The other doesn't have breast cancer when you do. I think the second one's worse. They're both not great. We don't like either one of those choices. Suppose that we know the following information about breast cancer and mammograms in a particular population. 1% of the women age 40 or older in this population have breast cancer. For women who have breast cancer, the probability of a negative mammogram is 0.03. I don't know if you caught it there, but that second one seems conditional on the first one there. So I think the first branch will be have breast cancer or not. The second branch is what's the test result, right? Negative or positive mammogram test. And so it breaks down those. Does she have breast cancer? So you would want to set up the tree diagram, right? Again, the first branch, the tough part there is getting that first branch is that. And then the second branch goes off of those from the given information. So a randomly selected, find the probability she actually has breast cancer, right? So for that one, that you actually have breast cancer, that would be which of these four ones would that be? So if you take the top one, so has breast cancer, oops, right, so the question was, randomly select a woman from age 40 or older from this population, test positive for breast cancer, find the probability that she actually has breast cancer. So if she tests positive, what's the probability that she actually has breast cancer? So you're going to look at a couple things. So first of all, how many folks tested positive? Well, you have to do 0.01 times 0.97. So you do 0.01 times 0.97. That's that top folks. So very much. Okay, so then test positive would be doesn't have breast cancer, so 0.99 times 0.06 test positive. So if we add those two numbers up, that's the folks that have tested positive. Whether or not they have breast cancer, that many folks, that percentage, 6.91% have tested positive. Let's read the question again. That she actually has breast cancer. So assuming she's test positive out of that 6.91, what percent actually has breast cancer? So that first number there, the 0.0097 is the ones that test positive and actually have it, right? So I think we're going to take, whoops, we're going to take that number, that's our numerator, divided by everybody who's tested positive, should be 0.14036. Let's see what happens if they do it. I haven't looked. 0.14, is that what we got? Yeah. So again, they showed their work there. They're taking both branches there, the top branch there and the third branch there. That's our denominator. And our numerator is the top branch there, if you look at the 4 different branches. Because that's the folks who have actually have breast cancer that tested positive. So again, just take some thought there and be careful. If you want to do a couple extra practice problems here, I'm just going to show you the answers for these two. Again, that first choice affects the second and the third choice because you're sampling without replacement there, right? So the first choice definitely has effect, and so you've got 15/20th times 14/19ths and 13/18ths. And then this one, draw a tree diagram. So there's your tree diagram, and then find the probability that the selected adult vapes. So you add up all 4 of those that end with vapes, right? So you're going to do all 4 of those multiplications out, add up those numbers to get 0.1463. And finally, this one, again, drawing the tree diagram is the toughest part, but then you got to use it, and then, got to figure out what they're asking for. And so, and answer the question. So virus was detected, you're adding up the top branch and the third branch there, that's the denominator. And then you're actually infected and the virus detected would be just the top branch. That's the numerator there. Okay, that's your lesson for today.